All right. Okay, so ladies and gentlemen, let's get started. So we left off last time. We left off last time talking about work and energy, and are we ready to begin? Yeah, you can wave to the camera. And we talked about, okay guys, try to act normal. I'm not gonna be able to use anything like that. And it's just one of those weird things. But I'm shooting a lot of video and I'm just choosing the best. That's one philosophy. The other philosophy is just shoot 2 or 3 and call it good. I'm gonna shoot a bunch and then use my best. So we talked about work and energy last time, the conservation of energy, and we did the skater. So Nate was on the skis, and then Nolan was on the half pipe, and Nolan wiped out on the half pipe. Yeah, and yes, you were on the snowboard, right? You were on the snowboard, and we remind ourselves, ladies and gentlemen, if somebody starts 10 meters up on the top of the half pipe and they go down, how high do they come up without friction? Yeah, the same 10 meters. However, if they go down the half pipe and then they do a middle jump where they're still moving horizontally, are they going to get to that 10 meters? Why? Yeah, they still have horizontal velocity, which means they still have kinetic energy. So all the potential energy they had up here in the half pipe will turn into kinetic energy down here and then back to potential energy up here. But if they have a jump in between, their potential will become kinetic, and then partway you'll have kinetic and potential, then back to all kinetic, then back to potential. Okay. That shake off the cobwebs? Okay. So we're done talking about work and energy. I want to make sure we're clear before we talk about power. Is there anyone who has any questions? Then we talk about power. Oh, right. Before we talk about power, the ramp. So consider a block here of mass 4 kilograms. It's at the top of a 5-meter high ramp, and the length of the ramp is unnecessary. Quick question for you. What is the change in potential energy if the block falls off the ramp? So lean over your neighbor and see if you can figure out what is the change in potential energy if we just go boop, and push the block off the back of the ramp. 200? How did you come about with that number? Good. So the potential energy is going to be delta PE, and that's going to be mass times gravity times change in height. Mass of 4 kilograms, gravity times 10, and a height of 5 meters. Normally, 4 times 10 times 20 is 200 joules. So it's going to lose 200 joules if it falls off the back of the ramp. And there's a little spider down here. It's going to do 200 joules of energy on the spider. Give me a thumbs up if you're with me so far. Okay, cool. Next. What is the change in potential energy if the block slides down the ramp? Maybe we should chat about that. So chat with your neighbor and see if you can figure out what would be the change in potential energy if the block slides down the ramp. If you believe it's 200 joules, raise your hand. Okay. If you believe it's less than 200 joules, raise your hand. If you believe it's more than 200 joules, raise your hand. Okay, good. Most of you realize that it doesn't matter if it falls 5 meters or slides 5 meters, the overall change in height is going to be the same. It's going to have the same mass, the same gravity, and the change in height will be the same. It's still going to be 200 meters. Next, what is the kinetic energy if the block slides down the ramp? In other words, what is the kinetic energy at the bottom of the ramp if it slides down the ramp? Same 200 joules? Why do you say that?
Wait, is the reference point at the bottom of the ramp?
Yes. Why do you say it's 200 joules? Yeah. Yeah, the total energy, which is going to be the sum of the potential and the kinetic. The sum of the potential and kinetic up here is going to be 200, which means the sum of the potential energy down here is going to be 200. This will really bake your noodle. If it falls off, we can calculate the speed at which it hits the ground. If it falls off the back, we can calculate how fast it's going to be going when it hits the bottom of the ramp. You know what else? That speed there will also be the speed down here, ignoring friction. But it has to go a lot farther. Yeah, it'll go a lot farther, but it'll also accelerate less. It'll take longer to get there, but it'll end up with the same speed at the bottom of the ramp there if it slid down the ramp than if it fell off the ramp. I'm going to demonstrate some really nifty piece of symmetry. Can we calculate how fast it would be going when it fell off the back of the ramp? Let's do that. We know that the change in potential energy is going to be a change in kinetic energy. And you told me it's 200 joules. What's the formula for kinetic energy?
1/2 mv squared.
1/2 mv squared. So, is this math you can do?
Yeah.
Yes.
So, let's find out how fast the velocity is.
So it's 10.
10 meters per second.
No, it's not 10.
10 meters
10,
per second?
10, not 10?
It's
10, 10?
10.
We can agree it's 10 meters per second?
Yes.
Here's the coolest thing, and I tricked you. I tricked you 6 weeks ago when I taught you kinematics. You could have done all the kinematics exercises, and Tyler knows this. You can do all the kinematics exercises with energy instead. Remember the 1/2 AT squared?
Yes.
If it falls 5 meters, that means it falls for 1 second. And something that falls for 1 second falls 10, 20, 30 meters per second. So if it falls for 1 second, it gets to the bottom, it's traveling 10 meters per second. One of the neat things about physics is you can do these exercises using different tools. So when Tyler takes the physics AP test and they give him an exercise where he has to find velocity of a falling object, he has the choice of doing kinematics, V equals AT, D equals 1/2 AT squared, or using energy, delta P E equals delta KE, because they both work. Pretty slick. Any questions about that? Yeah. Now you have those powerful tools. You can choose which one you want to use on the semester exam. Okay, what is the speed if it slides down? What is the speed if it falls down? And we can agree it's 10 and 10 either way? Yeah. It's going to be 10 if it slides down. It's going to take longer to become 10. It's only going to take 1 second if it falls down. It's going to take a little bit longer to slide down, but it's still going to be 10. All right. A couple more questions. How much force would be required to lift the block up the ramp? How much force? Force in newtons.
2,000.
What do you have to overcome to lift something?
Inertia. Friction.
This 1 kilogram mass has a something of 10 newtons.
A weight. A weight.
A weight. So in order to, if this block was at the bottom of the ramp and I wanted to lift it up here, what would I have to exert? 40 newtons. I would have to exert 40 newtons to lift the object up the ramp. How far would I have to lift it? 5 meters. 40 newtons lifted 5 meters gives me a potential energy of what? 200 joules. Now, if we had an angle, we could know exactly, guys, if we had an angle, we could know exactly how many newtons it would take to push it up the ramp. We don't have an angle, then can we agree it would be less than the 40 newtons? Yeah, and it would. And that's the basis for machines. We're going to talk about machines a little bit. Okay, questions? There are no questions, move on. Okay, try this. Here's a fun little exercise. You got another block here. You push a crate weighing 93 newtons up an inclined plane, pushing horizontally parallel to the ground with a force of 85 newtons. So in other words, you're going to push a block, a crate, up an incline. You're going to apply your force horizontally, and you're going to apply 85 newtons. You Imagine the scenario. First question. Oh, here we go. I guess both questions. How much work do you do? How much work do you do pushing the block up the ramp? So lean over to your neighbor and discuss this. How much work would you have to do to push this crate up the ramp? Tommy, do you have a question? Or are you an answer? Oh, okay. Dakota's got an answer.
I might be wrong as well.
Let's give Dakota 30 more seconds for everybody else to figure it out. Okay. Dakota, what is your answer?
All the work that I do is about 299.
299. Anyone else have an answer? I appreciate the answer. How did you come about 299?
I grabbed 5 years and then multiplied by 90.
Oh, okay. So in other words, you multiplied a diagonal displacement by a vertical vector?
Yeah, and then I multiplied by the inverse tangent of 3 over 4.
My goodness. Okay. So use the angle. All right. Let's avoid multiplying vectors that are not parallel to each other. So we have a displacement vector that is diagonal, and you multiply it by a vertical vector that is more vertical. So let's avoid doing that. Answer.
Wait, would you use W equals force resistance?
I would, yes.
So then I have 186.
186?
I think.
255.
Then 930 newtons equals, wait. Oh, would I convert the 93 to 930?
Okay. So I'm seeing a frequent misunderstanding. So a lot of people have the same misunderstanding. Let's think about the vectors here. In what direction are you pushing? Horizontally. You are pushing horizontally with 85 newtons of force. How far, or over what distance, are you pushing that 85 newtons of force? 4 meters. You're pushing it from the bottom of the ramp to the top of the ramp. You're exerting 85 newtons over 4 meters. What is the work you do? 340 newtons. Joules. 340 joules. Okay? So when you want to know how much work you do, you only really care about 2 things. The force and the displacement in that direction of force. In this case, 85 newtons, 4 meters. 85 times 4 is 340. Does that idea make sense? If it does make sense, answer the second question. How much work is done by gravity? 279?
279.
How did you come about with 279?
It's the force of gravity times the height.
So it's the weight that you have to overcome, the gravity, the weight you have to overcome, multiplied by the 3 meters that gravity acted against it. Technically speaking, you would be talking about this is the work done against gravity, or negative 279 joules. In other words, as far as gravity is concerned, you raised it 279 joules. You did 279 joules against gravity. You increased the potential energy by 279 joules. Yeah.
If you were pushing on the freight diagonally or something, then you would be fine.
Yes. Yeah. If you were pushing up the ramp, you'd have some other vector representing what your force applied would be. You'd multiply that by 5 meters. Yeah.
Wait, so why do we multiply by 3?
Because gravity only acts in the vertical direction. So the work done against gravity is the weight of the block, the 93 newtons, multiplied by how far we had to move it in that direction.
Okay, and we don't use any
No, because the crate is already given to us.
So,
The weight of the crate is already given to us.
and that's with gravity.
Yes.
Oh, okay.
If it gave us a mass of the crate, it would be 9.3 kilograms.
Okay.
Because it gave us the weight of the crate at 93 newtons, we just multiplied the 93 Newton crate by 3 meters. Okay. Does this stuff make sense?
Yeah.
Okay. So move on. Oh, springs. Okay, this is cool. The potential energy in a stored spring. It's a different kind of formula. It's a different kind of formula. And before we talk about it, we have to realize that when you start pushing on a spring, is it a constant force when you compress the spring? Say you're going to put a dart into your dart gun, your Nerf gun. When you start putting the dart in, do you apply the same amount of force at the beginning as you do at the end? No. How does the force change? Yeah. As the spring compresses, the spring pushes back more. So as the spring compresses, you have to apply more and more force. Does that idea make sense? Okay. Understand that energy stored in a spring is still still force times distance. Does that idea make sense? Okay, so let's diagram that for a little bit. So the diagram is pretty simple. You got your Nerf gun. Your Nerf gun's got a spring. You're going to apply a force on that spring. And as you apply your force, that force that you're going to have to apply is going to get larger and larger as the spring compresses. Make sense? Next, you're going to have to compress that spring a distance x. And that x is going to get larger and larger as you compress it. Does that make sense? Okay. So, understanding that idea, that the force increases as you compress the spring, the energy stored in a spring is a function of Hooke's law, which is as you apply force on a spring, you have to apply more force as you apply that force over a distance. The more you compress, the more force you have to apply. Does that even make sense? Okay. And it's given by Hooke's law. The negative sign is there because Hooke's law is technically telling you about the restoring force. In other words, the force the spring pushes back. So Hooke's law tells us the spring force, or the restoring force, the force you have to overcome to compress the spring, is a function of the spring constant, how tough the spring is, and its displacement. The springs in your car have a constant in the thousands. The spring in your ballpoint pen and your mechanical pencil have a constant in like the tenths or even the hundredths. So to give you an idea, a really high spring constant means a very stiff spring. Okay, so that's Hooke's law. So the energy stored in a spring, the work required to store that energy in a spring, is a function of Hooke's law, the force you have to apply, and what? Work is what times what? Force times distance. So you need another x, because work is force times distance. You need another x representing how much force you have to apply, and because the force is not constant, it starts small and gets big, we throw a half in there. Because it turns out to be a linear relationship. In other words, if you're going to compress the spring twice as much, you're going to need twice as much force. Twice the displacement requires twice the force, so it's a linear relationship, which makes a fun little triangle. And that's where the 1/2 comes from. The energy stored in a spring is 1/2 kx squared. This is called elastic. This is called elastic potential energy. So the kx, that's the work that you do. The second x is the displacement for the work. So what you're really So what you're really looking at is Fxx. F is Kx, Xx, and then the half is there because you start pressing on the spring, you apply a little bit of force first, and you apply more and more as you compress the spring. That is the energy stored in a spring, 1/2 kx squared. If you're up front, it's also on the ball. Right up there, right up in there. Okay, questions? If there are no questions, I have a sample exercise for you.
Ooh.
Are there any questions? Here's your sample exercise. Consider a falling block. So we're going to drop a block. Boop. We're going to drop a block, and we're going to drop it onto a spring. You see the block? What color is the block?
Yellow.
It's a yellow block. We're going to drop the yellow block onto a spring. Now, the block is up over the spring. We're going to make the spring the reference point 0. So the block has what? Potential energy. The block has potential energy. I'm going to be like, that's a nice yellow block. I'm going to aim it at the spring, and I'm going to release. When I release it, what is that potential energy going to turn into? Kinetic energy. Right as it hits the spring, that kinetic energy is going to start turning into what? Elastic potential energy. So we have gravitational potential energy up here. It starts falling, turns into kinetic energy. The moment it touches the spring, it's going to start turning that kinetic energy into elastic potential energy. Now, the reason I mention that is sometimes we just skip over that Ke. Sometimes we do Pe to Ke. Sometimes we do Pe grav to Pe spring. And that's what we're doing today. We're going to turn the Pe grav into Pe spring. So, how much would a spring with a constant of 200 compress if a 2 kilogram mass is dropped on it from 1 meter above? See if you can figure that out. How much would that spring compress if you dropped a 2 kilogram mass from 1 meter above? Question or the answer?
Well, a question.
Okay.
What is the displacement of spring potential referring to? Is it like from just spring when it's fully out to when it's compressed in?
Yeah, when the equilibrium point of the spring is taken at its stretchiness when all it's supporting is its own weight. Does that make sense? So if you have an unstretched spring, its 0 point is at the top when all it is supporting is its own weight. If you turn it over, then you measure a new point when it's supporting its own weight. So we're basically saying the unstretched is the top of the spring, squished is the difference between that unstretched top and that squished top. Question or answer? Okay.
The spring force, is that just straight up the potential energy, or do you need to plug that back into the W equals F equals to find the force?
Can you repeat that?
Well, I'm trying to find the spring force for F, and F equals A KX.
Oh, you're not going to need to.
You don't need to.
No. Because what we've done is we've taken a block that has potential energy, mgh. And we're going to skip over kinetic energy. We know it's there, but we're skipping over it. And all the gravitational potential energy is going to become elastic potential energy. So when you set everything against each other, you have all the numbers you need. So specifically, you have mgh equals 1/2 kx squared. All the gravitational potential energy becomes elastic potential energy. Question or answer?
Question. So we're finding X.
We're finding X. Yeah, we're solving for X, which is the compression of the spring. Question or answer?
More of a guess.
No.
Well, I was
Okay, well, let's wait a little bit. Are you looking at me with blank stares because you've got the answer, or you want me to solve it for you? Second one. Come on, you can do this. You can do this. So, potential energy becomes gravitational potential energy. We're assuming it's on Earth. I gave you the mass of the block. I gave you the height above the spring. I gave you the spring constant. You can solve for X. Do you give me an answer?
Square root of 1/5.
Square root of 1/5?
Yes. 0.45.
No. Oh,
Yeah, square root of 5. 0.2? Okay. Well, let's see. We have a mass of 4 kilograms. We're assuming it's on the planet, so we're going to use 10.
Don't we have mass of 2 kilograms?
2 kilograms? 2 kilograms. Let me just read here. Mass of 2 kilograms. Thank you. We're assuming it's on the planet, so we use 10. And the height above the spring was 1 meter. 1/2. The spring constant is 200. And then x squared. So this side looks like 20.
Yes.
And this side looks like 100. X squared. So x is the square root of 20 over 100.
Yes.
Which is the square root of 0.2, which you're telling me is about 0.45?
Yeah.
Yeah, 0.45.
Yeah, sounds good. Okay. So that's it. Can you follow this math?
Yes.
All right, cool. So that's it. So if we took a block and we held it over a spring 1 meter high, we dropped that block, all of its potential energy becomes kinetic energy, and then all that kinetic energy becomes gravitational potential energy. Yes?
And the answer is saying it would go down 0.45 meters.
Yes. From unstretched to squished, it would be 0.45 meters. That difference would be 0.45 meters. Now, we all know in real life it would bounce and might launch it back up again, but all we really care about is how much is it going to stretch. Give me a thumbs up if you're with me so far. Okay, next. What if the same block struck the spring horizontally while traveling at 3 meters? So maybe it's flying, maybe it's on a frictionless plane. Same block is traveling 3 meters per second, and it strikes the spring horizontally. Turn the whole thing 90 degrees. Now what kind of energy is going to turn into elastic potential energy? Kinetic energy. So go ahead and do that. Gesundheit. Woo!
I said it first. Actually, I said it first.
Point 3. Did anybody say it with style? 0.3! Hey! Okay, so the same block has a mass of 2 kilograms and a velocity squared, and then this is going to be 1/2 kx squared. I love it when 1/2s cancel out, don't you?
Yeah.
So this is 2 times velocity. We said it was 3 squared, and that's 200 x squared.
Which gives you a square root of 9 over 100, which is 3 over 10, which is...
Square root of 9 over 100?
Yes.
Wait,
Which is 18 over 200, which if you make it 9 over 100, it's better that you can actually take the square root of it by hand.
Fair enough. Okay. So this is 18, and this is 200x. So x is the square root of 18 over 200.
Which
Do
is
that
the-
math.
Which is the same as 9 over 100.
9 over 100.
Which that you can solve out by hand. That's what I was saying.
And you said it's 0.3.
0.3.
0.3. Okay. So, are we cool with this idea? This conversion of energy stuff? Okay.
Yeah.
Well, the good news is at this level of physics, the conversion is going to be very, very clean. It's going to be all of one kind of energy to all of another kind of energy. The spring's not going to be moving. Okay. We're not going to drop it and have part of the energy turn into this elastic. So all of the energy will turn into elastic, or all of the elastic will turn into potential energy. This is like dart guns, your Nerf gun firing out. So, question?
So if it's horizontal, it's kinetic, and just vertical, we're just doing potential.
Well, that's a good question. This is kind of what I just mentioned. If you took your block and you threw it down, then you would have both kinetic and potential to begin with. Now it would turn into elastic. But in this course, we're just going to drop everything onto springs. So it's going to be all gravitational to all elastic. Okay, so I don't write anything down here. This is kind of fun. Just want to mention this and plant a seed for momentum. Momentum is our next unit, and it's all about collisions. So when we're doing momentum, if you have a collision where the initial energy is the same as the final energy, we call that an elastic collision. An elastic collision, same word, slightly different definition of elastic potential energy. An elastic collision is when all of the energy of all the objects before the collision is equal to all the energy of all the objects after the collision. Pool is a pretty good example of this. Atoms collide mostly elastically too, but very few things actually collide elastically. So, in reality, elastic collisions don't really exist. How do you know? Yeah. Correct. Not only would there not have to be any friction, there would have to be no friction between the molecules, so you would have no expansion of the molecules. In other words, you would have no shock wave when things hit. So, if you could play pool in space, where there would be no expansion of the molecules, then you could have an elastic collision. But in reality, that clack, when things hit together, that's using energy. And the rubbing on the felt, warming the felt up, that's using energy. But yeah.
A game of pool is freaking crazy.
Yes, it would. Okay, power. From your reading, what is power? What is it? What is power? I've got the power!
It's overnight.
Right, it's overnight. What is power?
It is 12 times work.
Okay. No, but it's a good guess. If you said, my engine is very powerful, what does that mean? It can exert a lot of force. The motor that spins the Space Needle in Seattle is about this big. It turns the entire top of a building. Is it very powerful? Turns out it's not. Because in addition to being able to apply force, we also care about what? Horsepower. Okay, so horsepower is power. My little Honda Civic can get my car to 100 miles per hour. It takes a long time. You do the same thing in a Porsche, it can get to 100 miles an hour in like 6 or 7 seconds. Which one's more powerful? The Porsche. So what is missing in our discussion of power? Time. Time out. So power is the rate at which work is done. Power is the rate at which work is done. It is quite simply work divided by time. I could push my car down the road. A few of us would probably get it to Henderson. But it's going to take a long time. The engine's a lot more powerful than we are. So power is the rate at which work unit of power is the watt. What? 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 What you what? What's up, Doc? Yeah. A watt is a joule. A watt is a joule per second. 1 watt is the work of 1 joule done over 1 second. It's kind of nice, standard units. The standard unit for work is a joule. Standard unit for time is the second. So the watt is a joule per second. Yes, and a gigawatt is a billion of those.
How can we tell the difference between watt and work?
One is a variable and one is a unit. Yeah, this is why we don't use weight. We don't use W for weight anymore, because we have another W. When the W is a variable, it's power. When the W is a unit, it's a watt. So if it follows a number, it's probably a unit. If it's in an equation, it's probably a variable. So the watt is so small, it really is really small. The watt is so small, we usually use kilowatts. Motors in the UK, motors in Europe are rated in kilowatts, not horsepower. We rate them in horsepower because we're weird. We like the imperial system, we don't have to change. But in Europe, they rate engines in kilowatts. And here's a fun fact. When your parents buy power from the power company, they're not actually buying power. They are buying units called kilowatt hours. A kilowatt hour is the amount of energy equivalent to 1 kilowatt exerted over 1 hour. And it should make sense that if power is work times time, then if you multiply power times time, what do you get?
Work.
Work, or energy. I'll say it again for those who weren't paying attention. Guys? If power is work over time, if you multiply time by power, what you end up getting is work. So if you take a kilowatt, 1,000 watts, and multiply by an hour, 3,600 seconds, what you get is a kilowatt hour. It's a packet of energy that is sold to you for you to use, to heat or cool your house, or power your Xbox. It's about a dime, about 10 cents. It is equal to a certain number of joules. Who knows how many joules, besides Tyler? Who knows how many joules a kilowatt hour is? Close. It's 1,000 watts times 3,600 seconds.
36 million?
3.6 million joules. A kilowatt hour is 3.6 million joules. It's not a bad deal for a dime. One dime gets you 3.6 million or something. Not too bad. Questions? All right, moving on. So, on your own, I'm going to give you 3 scenarios. Tell me which of these exerts the most power. A winch that pulls a weight of 1,000 newtons, 20 meters in 300 seconds, like what's going on out there right now. A basketball player that shoots an 8-Newton ball straight up 3 meters in half a second. Or a soccer player that kicks a 6-Newton ball 4 meters, 0.3 seconds. Which one has more power? Can I tell you the power of each of these? Which one's got the most power? When you're done, compare your answer with your neighbors. And you can assume everything's moving straight up, just so we can keep all the vectors lined up. Already? Okay. Did you compare it with Derek and Nate?
Yep.
No, wait a little bit. Got the answer?
No, are we using P equals W?
Yep, P equals W over T.
Work is force.
Power is work over Power is work over time. You take 30 more seconds. Then we'll vote. We got a winch and a pulley. We got a basketball player. We got a soccer player. Which one is most powerful?
Wait, we're gonna take a vote.
10 more seconds. Okay. If you believe that the winch is the most powerful, nobody. If you believe the soccer player is the most powerful, yeah, soccer player. It is. Winch, 67 watts. Basketball player, 48 watts. And a soccer player, a big fat 80 watts. But in a soccer player, he can't beat up a winch. A winch is a machine. Yeah, it works slow. You seen these little winches on the front of van, or like trucks that are about this big? Tiny little motor. What it does over a long period of time. But work is not just the force it can lift, it's also the time. Questions? Then we leave our discussion with machines.
Yeah.
Machines are objects that change the direction or magnitude of force, but not the work done. A machine changes the magnitude or the direction of force, but not the work done. Ideally. Meaning without friction. With friction, real life kicks in, but a simple machine is something that changes the direction or the magnitude of force, but not the work done. I happen to have some machines over here. Okay. If we're ignoring friction, the work we put in, the input work, should equal the output work. If we're ignoring friction, the input work should equal the output work. The input work is called the effort force and the effort displacement, and the output work is called the load force or the resistance force and the resistance displacement. And hopefully, these two things are the same. In this class they are, because we don't do friction, and we don't have to. I have here 3 pulley systems.
A pulley's a machine.
A pulley is a machine, yeah. And we're going to investigate pulleys in and of themselves next week. But in this pulley system, I have a 500 gram mass, 5 Newton gram weight, over a pulley connected to another 5 Newton weight. Notice what happens. When this one goes up, this one goes down. This is an Atwood's machine. We talked about Atwood's machines last unit. What can you say about how much A goes up when B goes down? Yeah, they're equal. However, on this side, here I have a 1 kilogram mass, and I have 500 grams here, half a kilogram. Notice what happens when the 5 kilogram goes up and down. Yeah. since the 5 Newton goes up and down, is how much more compared to the 10 Newton? Yeah, it's half as much. It has twice the mass. Sorry, this one has twice the mass, so this goes half as far. This one has half the mass, it travels twice as far. See how that works? Now this is that same 1 kilogram, and this is 350. I don't have 330, so I had to go 350. Friction takes care of the rest. Look what happens to this one. Yes, it does. Well done. Yeah. So, because this weighs 1/3 as much, it has to travel 3 times as far. And here's the secret. If you look at the number of rope segments supporting the weight, that's called the mechanical advantage. Mechanical advantage is a ratio of the force of the effort to the force, or the force of resistance to the force of the effort. And the number of rope segments supporting the weight gives you the mechanical advantage. This has 3 rope segments supporting the 1 kilogram mass. This pulley has a mechanical advantage of 3. This has 2 moving rope segments supporting the mass. It has a mechanical advantage of 2. And this has only 1 rope segment supporting the mass. It has a mechanical advantage of 1. That's not really useful to us other than changing the force, changing the direction. That's everything you need. So the physics is the FEDE equals FRDR. The shortcut is if you know how many rope segments are supporting the weight, that's going to be the mechanical advantage. Now, if something has a mechanical advantage of 4, it can support how much more weight? 4 times. Excellent. So that means it's going to move how far? 1/4. Okay. I was done, so yes.
What's the rope segments you're talking about? Is that the pulley?
Yes.
The number of rope
The number of rope segments connected to the pulley.